the present session, we have to talk about non-vanishing condition of CG coefficient, which is also called as triangular rule. To arrive the triangular rule, we should start our journey from the coupled representation J1, J2, Jm. This coupled representation J1, J2, Jm is expressed in terms of Klapskaran coefficient summation of m1, m2, J1, J2, J, m1, m2, m multiplied by uncoupled representation J1, J2, m1, m2. Say this is equation number 1. It is known as the coupled representation is expressed in terms of uncoupled representation by means of a transformation coefficient called CG coefficient. In order to arrive the triangular rule, we have to operate the left hand side of equation 1 by the operator Jz. Jz, J1, J2, Jm is equal to summation of m1, m2, J1, J2, J, m1, m2, m, and the right hand side is operated with Jz plus J2Z. These are all operators. Z component of the first system, Z component of the second system. J1Z plus J2Z is allowed to operate on this eigenfunction J1, J2, m1, m2. Here this eigenfunction is in the uncoupled form, whereas the left hand side eigenfunction is in the coupled form. So this is equation number 2. Now the eigenvalue of Jz is mh cross. So this is mh cross and the same function J1, J2, Jm, which is equal to summation of m1, m2, then J1, J2, J, m1, m2, m. Then the eigenvalue of J1Z is m1h cross, whereas the eigenvalue of J2Z is m2h cross. So this is m1 plus m2 into h cross, and there is multiplied by J1, J2, m1, m2. Here this is equation number 3. H cross is present on both sides, so we cancel h cross. At the same time, the value of J1, J2, Jm, m into J1, J2, Jm is expressed in terms of CG coefficient and uncoupled representation. So summation over m1, m2, J1, J2, J, m1, m2, m, and uncoupled representation J1, J2, m1, m2. This is equal to the same right hand side. Summation over m1, m2, J1, J2, J, m1, m2, m multiplied by m1 plus m2 into J1, J2, m1, m2 in ket space. So this is equation number 4. H cross cancelled out, so without H cross we are returned. At the same time, this coupled representation is expressed in terms of CG coefficient and uncoupled representation. Both the sides, the CG coefficient and the eigenstate J1, J2, m1, m2 are present. So this is modified as m minus m1 plus m2. The entire is multiplied by CG coefficient m1, m2 into J1, J2, J, m1, m2, m into J1, J2, m1, m2, which is equal to 0. This is equation number 5. Now, from equation 5, we may point out that for non-vanishing CG coefficient, the value of m minus m1 plus m2 should be equal to 0. Therefore, m is equal to m1 plus m2. From equation 5, for non-vanishing CG coefficient, the value of j1, j2, j, m1, m2, m not equal to 0, and the eigenstate is also not equal to 0. Therefore, the quantity m minus m1 plus m2 equal to 0. That is, m is equal to m1 plus m2. For non-vanishing CG coefficient, the value of m could be equal to m1 plus m2. If m not equal to m1 plus m2, the CG coefficient vanishes. For the given value of J1, M1 can have 2 J1 plus 1 values. Suppose J1 is equal to 1. If J1 equal to 1, M1 can have 3 values. 2 into 1 plus 1, 3 values. The M1 values are plus 1, 0, minus 1. In general, we can write the spectrum of M1. The spectrum of M1 is J1, J1 minus 1, J1 minus 2, then the final value is minus J1. This means that the maximum value of M1 is J1 and second maximum value of M1 is J1 minus 1 and the third maximum value of M1 is J1 minus 2 and the minimum value of M1 is minus J1. Now, the minimum value of J1, the minimum value of J1 is minus J1 and is expressed as J1 minus K is equal to minus J1. See here, the first highest value of M1 is J1, then next value is J1 minus 1, next value is J1 minus 2, this series is going on and ended with the lowest value of minus J1. Therefore, J1 minus K is equal to minus J1. From this, K equal to 2J1. The same manner, for the given value of J2, M2 can have 2J2 plus 1 values. The spectrum of M2 is J2, J2 minus 1, J2 minus 2 and this is ended with minus J2. The highest value of M2 is J2 and the lowest value of M2 is minus J2. The lowest value of M2 is J2 minus K, which is equal to minus J2. Therefore, K equal to 2J2. If you substitute K equal to 2J2, we can get J2 minus 2J2 equal to minus J2. In this way, we have arrived at the values of M1 and M2. In the same way, for the given values of J1 and J2, M can have 2j plus 1 values. Here j equal to j1 plus j2 equal to m. Now the spectrum of m is j1 plus j2 comma j1 plus j2 minus 1 comma j1 plus j2 minus 2, and the final value is minus of j1 plus j2, because the value of lowest value of m1 is minus j1, lowest value of m2 is minus j2. So this is m1 plus m2 with a negative sign. This is minus j1 minus j2. It is equal to minus of j1 plus j2. Because the lowest value of m1 is minus j1, the lowest value of m2 is minus j2. So minus j1 minus j2. If you take minus sign outside, j1 plus j2. This is the lowest value of m. We know that the lowest value of m is arrived by the lowest value of m is arrived by the formula j1 plus j2 minus k. Already we have had two values for the k. One is 2j1 and the another one is 2j2. These are the two possible values. For in the case of m1 we have had the value of k is j1. In the case of m2 we have had the value of j2. 2j2. The value of k is 2j1 in the case of m1. In the case of m2 the value of k is 2j2. Therefore, if k equal to 2j1, j1 plus j2 minus k is equal to j1 plus j2 minus 2j1. This is equal to j2 minus j1. This is the lowest value of m. M is equal to j2 minus j1. This is one case. Or lowest value of m or lowest value of j, all are same, m equal to j. If you take, if k equal to 2j2, then j1 plus j2 minus k is equal to j1 plus j2 minus 2j2. See here, this j1 minus j2, m equal to j equal to j1 minus j2. So j can have two values, j2 minus j1 or j1 minus j2. So in general, the lowest value of j is modulus of j1 minus j2. Highest value of j is j1 plus j2. The lowest value of j is j1 minus j2. With the help of this, we can develop the condition called triangular rule, which is suitable for non-vanishing CD coefficient. See that the value of j should be greater than or equal to modulus of j1 minus j2, greater than or equal to modulus of j1 minus j2, less than or equal to j1 plus j2. If this condition is satisfied, the CD coefficient is not vanished. This is called as a triangular rule. J, the total angular quantum number, should be greater than or equal to J1 minus J2 more or less, or less than or equal to J1 plus J2. This is called as triangular rule. Since this is identical to the three sides of a triangle, delta of J1, J2, J is called the triangular rule, which explains the non-vanishing condition of CG quotient.